So, while it must have been very exciting to systematically derive the skip command, obviously if that's all we can do, that's not going to be very exciting for very long. So let's look instead at how to derive a simple, another simple command, assignment to a simple variable. And all along, keep in mind that the purpose of the game is to determine command S where the precondition Q and the postcondition R are already given. And let's return to a very similar example as we used in the skip command video. And here what we have is that x is equal to 0 and some count c is equal to its original content c hat. And what we want to do is end up in a state where c is still equal to 0 and the count is incremented by 1. Or if x is not equal to 0, then the count should remain the same. So this might be the second half of an if statement. Again, you could just guess at what this ought to be, and then you could come back and prove it to be correct. And if then it is correct, then everything is okay. You have used the precondition and the postcondition to guide you towards a correct command, and that's just fine. Or again, we can do it a little bit more systematically, and let's learn how to do that. Part of the problem statement is that the counter c is the only variable that's allowed to change value. So you may know this from context in the program that you're trying to derive. And that then leads us to say, well, that variable should be assigned some value, the expression e, where we use this funny looking e for the expression. And then what? Well, we don't know what the expression is, but we do know how to compute the weakest precondition. That's a matter of substituting the expression e in for every occurrence of c. Strictly speaking, we probably should have had some parentheses here, but it's all going to be okay. And now what? Well, now you just stare at the first 3 lines of this code segment. You want to use what you know about Q and the fact that Q has to imply the weakest precondition to now determine what that expression must be. Well, if you look at the second part of this disjunction, you kind of know that that's just not going to work, because x is originally equal to 0, x is not allowed to change its value, and x can therefore not become non-zero. So that part we are going to ignore, and instead we're going to look at this part of the disjunction. If we can now choose our expression e such that what we have highlighted here in yellow is exactly the same as q, then by weakening strengthening we know that q implies the weakest precondition. And how can we choose our expression e? We're going to show you 2 different ways. One way is to say, well, if we choose c to be c plus 1, then the plus 1 on both sides of the equality will cancel, and then you just get c equals c hat back, which then means that that part of the disjunction is exactly q, and then we are exactly where we want to be. So, guided by that, we choose our expression to be c plus 1, and then we know that we can subtract plus 1 on both sides, and then we know that q implies the weakest precondition, and therefore we have a correct code segment. So we now have determined that that expression should be c plus 1. The way Maggie prefers to do it is as follows. We know that it's that left part of the weakest precondition that is going to guide us. In that left part, the expression must be equal to c hat plus 1. So why not just pick the expression to be c hat plus 1? Well, the problem with that is that c hat is really a variable that was introduced to capture the original value of c, so that we can also use that original value in the postcondition, and therefore we can't compute with it. But we notice from the precondition q that c hat is actually the content of variable c. What that means is that we can just compute with c instead, and we notice that our expression becomes c plus 1. And then we can go ahead and plug that into the weakest precondition, and we notice that Q implies the weakest precondition, and everything is great. So in summary, when trying to derive a code segment to be correct, where the precondition Q and the postcondition R are given, and only one variable, let's say x, can change value, what you do is you pick your command to be x becomes some expression. You then propagate that expression into the weakest precondition, and then you pick that expression such that the precondition implies the weakest precondition. And along the way, if you end up computing with what I call a dummy variable, something that denotes original contents, then you need to somehow find a way to use a value that actually is stored, as opposed to this value that's only introduced for the sake of reasoning about the program. Now, what if we go back to the example from the previous unit? What if we didn't recognize that we could just use the skip command? Well, we could simply say, we still know that c is the only variable that can now change value. We can therefore set it equal to some expression. We can propagate it along into the weakest precondition. We can recognize here that the precondition is more likely to imply the right part of the weakest precondition rather than the left part. Why? Because here we said that x is not equal to 0, and we're not going to change the value of x. And then through the same kind of reasoning we just did, we can conclude that the expression should be just c. And then we recognize that if you assign c to c, you might as well execute the skip command. So this is an alternative way of deriving a command that turns out to be the skip command. What I want you to do next is do this homework, where you're simultaneously assigning two variables s and t. And if you look at the precondition and the postcondition, what they tell you is that the values of s and t should be swapped. I'll see you in the next video.